Thanks for taking the time to go a little bit deeper into the readers' questions on my latest blog about write back versus write through. Thanks. Since I was at headquarters, I thought instead of writing the blog, I thought, oh, let's ask you and go into more detail about the process itself, right? So before we go into detail, let's cover the basics first, right? So let's see what's write through and what's write back. So let's say you have a virtual machine and it's running on an ESX box accelerated with FVP, right? And then you have your flash device, and then all the way down you have your array, right? So when we configure the virtual machine with a write-through policy, the I/O is sent to the ESX server, it's being forked, it goes to the flash device and it goes to the array. They both acknowledge it, and then the application gets the acknowledgement, right? So this is write-through. Now in write-back, the virtual machine goes, sends the I/O to the ESX box, and FVP sends it to the flash device and it acknowledges it back to the virtual machine. In the meantime, the I/O travels all the way down and goes to the array. So can you elaborate a little bit more about the timing of the de-staging area?
Sure. So I guess by de-staging area, just to kind of maintain continuity from your blog post, you're talking about the writes coming in from here, making it to the flash device, and they're all held out here.
Yeah.
And this area is called the de-staging area. And then eventually we are going to asynchronously write out these writes that we have collected into the array.
Yeah.
And so the way we do it is the de-staging area is active as soon as the VM does writes. And this asynchronous write out to the array is active as soon as we have something in the de-staging area. Okay. So in other words, there's no collection of IOs that we kind of wait for before we start writing. It starts as soon as possible. The only thing we take care of is to not overwhelm this connection, because as you know, it's a little fragile connection, as if you try to perturb the queuing, etc., then the array is just going to be overwhelmed. So the big deal about write back is the fact that the virtual machine could be doing this I/O. Let's say this is IOPS,
yeah,
and this is time.
Yeah.
And it could be doing spikes and then going all over the place. And by virtue of write back, because we are de-staging and we are de-staging at a very constant pace, so as not to overwhelm this link,
yeah,
what the array sees is that.
Okay.
Is if this is IOPS and this is time as seen on the fabric, then it sees a very constant rate of IOPS, which is not this, it is not this, it is somewhere in the middle.
Okay.
And so in effect what you achieved is you've actually ironed out the traffic that the virtual machine generates into a very steady rate of input into the array, which the array can actually react to very well.
Okay.
As opposed to that, where the array gets overwhelmed in this parts and then the array is too idle in this parts.
Okay, so what happens if let's say that there's a lot of external workloads going on in the array, and this stable amount of IOPS is actually overwhelming the array? It's possible, right? So how do we do when we send the IOs too fast for the array to actually process?
That's a good question, and so it's a input-output problem. Is eventually if the virtual machine is extremely write intensive and it's writing new stuff at a very rapid pace, then you might have to do fancy tricks, which it turns out we do.
Okay.
And so the way to understand that is maybe let's say here's the latency curve, and what the virtual machine sees as effective latency. Well, let's talk about flash latency. So the virtual machine is doing these writes, and ideally it'll get really low latency, which is flash class, because all the reads and writes are being absorbed out here. The SAN might be doing this latency, and it might be slightly more variable. And what the virtual machine sees effectively is this. because the writes are acknowledged to the virtual machine as soon as they're put in flash. Now, if we realize that we are not able to hold all the writes, all the pending writes for the virtual machine in this destaging area, what we are going to do is inject an artificial delay into every time we acknowledge a write to the virtual machine.
Okay.
And so what that does is it'll take the applications, this is the SAN latency, it'll take the application's latency slightly higher than flash. It's still much better than the SAN. Yeah. And we are going to use that extra time to try to empty out the destaging area. Okay. Now, if this time is not good enough, maybe we'll inject some more delay and we go here. And so it's basic queuing theory is, we keep on throttling the rate at which we are acknowledging the writes, and we keep that latency somewhere between flash and SAN so that we get a better chance to destage all the writes to the array that we've actually accumulated in the destaging area. The net effect is that eventually you don't have to do much, as you are presenting a write workload, and FVP will tune the acknowledgement range of writes to the virtual machine such that the destaging area can stay at a reasonable size, and at the same time the virtual machine is able to do more and more writes.
Okay. So we talked a lot about destaging area, and these are writes, but we also accelerate reads. Mm-hmm. So what about the sizing of the cache? Do we need to set any sizing per virtual machine, or can you tell me a little bit more on how FVP does this?
Sure. So the first thing we did is there is no sizing for the user to worry about, right? And that was very important because people can hardly understand everything that an application does, and so to actually have to understand it for every virtual machine that you're running, for every workload, is just too much to ask, and it's just operationally infeasible. So we manage the space that a virtual machine uses on the flash device on a per VM basis, and then you can imagine that different VMs, let's say if you have another one, it is using some other part of the flash device and so on. And then we automatically try to balance out what virtual machine gets what amount of flash device, depending on what is the efficiency at which it's using the flash device, and depending on the relative priorities of virtual machines and so on. That's really what the FVP resource manager is out to do. But in general, all that aside, from an implementation point of view, the way to think about space with FVP is that, let's say this is the space used by a virtual machine on flash. And so part of that space is read-only data. In other words, data that the virtual machine has read or written in the past. But this is not data that needs to be written out to the array. This is not part of the destaging area. Okay. And then there is the destaging area. Yeah. And so this is constantly accumulating writes from the virtual machine. This is all data that you use to service reads. And as we destage, as we write these things out to the array, the destaging area is promoted to this area. Okay. And so this boundary is constantly moving, right? At the same time, the virtual machine might be doing more writes, and so this boundary is constantly moving too. And so new writes are coming into the destaging area, and that makes the new destaging area. And then the old writes, which have already made to SAN, are now getting into the immutable area that we can use as the read acceleration part. Okay. And so now, the way eviction works, or space management between virtual machines works, is that, well, the destaging area is pinned, because unless you have written this stuff to the SAN, you can't afford to lose it. But this area is up for resource management. And so now on a per virtual machine basis, we figure out what are the hot regions. So let's say these are the hot regions and these are the cold regions. And so we prioritize which parts to keep, which parts to evict in case you run out of space. Okay. on the flash device. And well, that's roughly how it works. There is the part that can never be evicted. There is the part that can be evicted based on the IO characteristic of the application. and it's a very dynamic boundary between the two parts. Is this part is being converted into this part as we write out to the SAN.
Okay, so we are in the business of handling data, right? So one of the questions was, can we provide more information about data corruption when using write-back and replicas?
Right. Well, I've been in this business for 10 years, so yes, it's a reasonable question. Is every time something is in the IO path, one has to worry about whether it is keeping data consistent. And so we've attacked it by using a few ways, right? From a tactical point of view, what we did was we ran a really long beta program, as you're aware. And every beta copy of FVP that shipped actually went out with diagnostics. And so the first thing that FVP tried to achieve in the beta cycle was to make sure that correctness is ensured. And so there was a lot of debugging code to make sure that what we are writing out to the SAN is exactly what the application wrote out to the SAN.
Okay.
And what we are reading is what we are reading, providing to the application from this or that is exactly what the application expects if we were not in the way, and so on.
Okay.
So that's how we solved it from a kind of go-to-market point of view. Is you run a beta program and you focus the beta on correctness rather than performance. Although the performance was very good, as you've seen on Twitter, but there was a lot of correctness measures, so to speak, that we put in. The other thing we did was, we have a lot of folks, including myself, who worked on the ESX storage stack, so we understand this very, very well.